Good morning, good afternoon, good evening from wherever you are joining us from, and a very warm welcome to you all. It's great to have you join us for today's session, which is a talk on introduction to quantum computing and quantum programming in PennyLane. We are very thrilled to have such a passionate and eager group of participants for this course. And today we are not just learning about quantum computing, we are stepping into the realm where the ordinary actually becomes extraordinary for us. And we are very honored to have a very resourced personnel with us today. Before I introduce him, I would like to urge you all to make use of the chat room to ask your questions. If you have a question as well, you can as well use the raise hand button to raise your hand, and we'll kindly invite you to unmute yourself and ask your question, please. Do not hesitate to ask questions and get involved and follow up with everything we have today. Thank you once again, and a very special welcome to our speaker as well. So like I mentioned earlier, we have a very resourced speaker today. He is a quantum computing educator at Xanadu, where he helps educators worldwide train the next generation of talents in quantum computing and incorporates PennyLane into university curricula, which you are a talent as well today. He holds an MSc in physics from the University of Toronto with a research focus on ultra-cold atomic physics. He holds a PhD from the University of Toronto as well, specializing in single molecule biophysics. After a brief postdoc, Daniel taught physics and engineering in various departments within the University of Toronto before joining Xanadu in 2023. This might interest you, especially those of us who would like to be mentored by him. His area of research interests are ultra-cold atomic physics, single molecule biophysics, quantum computing education. We are very fortunate and privileged to have with us Daniel Felipe Nino. Daniel, please, you are welcome to our e-learning platform. Thank you so much for honoring our invitation.
Thank you, Dorcas. Hi, everyone. It's a pleasure to be here today. Let me start by trying to share screens, make sure that works. Okay, can you just confirm that you can see the shared screen? Just with a thumbs up or something in the chat. Okay, yeah, so it's a pleasure to be here. I want to thank the eLearning African International School on Quantum Science and Technology for organizing this and for inviting me to talk to you a little bit about quantum computing, PennyLane, and what we're doing at Xanadu in terms of quantum computing. So part of this talk is going to be a little bit interactive. I'll give you some guidance on how to do that. But if you got the instructions from Henry on Google Colab, we'll make use of that later on in the talk. So as Dorcas mentioned, I work at Xanadu. Xanadu is a quantum computing company based in Toronto, Canada. We were founded a little less than 8 years ago, going on 8 years in about September. We're headquartered in Toronto, in Canada, and we recently surpassed over 200 people working at the company. So we've grown very quickly over the past couple of years, and we're all driven by this mission of building quantum computers that are useful and available to people everywhere. And there's several facets to that. What we do to accomplish this mission is we take a full stack approach to quantum computing. What that means is that we're building photonic quantum hardware. We're pursuing a photonic architecture to quantum computing. We are actually primarily a hardware company. On top of that, we're also pioneering quantum software, PennyLane being one of those software libraries that we're developing, the main one really. And we're also involved in a lot of quantum algorithms research and development. So trying to work out which algorithms or which problems are amenable to quantum computers and how to develop algorithms that can take advantage of hardware as it's being developed. So I'll start off with a relatively brief introduction to quantum computing. I understand many of you are new to quantum computing. So I'll give you the main ideas. It probably won't be enough for you to really understand quantum computing, but I hope it gives you a flavor and piques your curiosity so that you can pursue further study later on. So what quantum computing is ultimately is a new type of computation that looks to harness properties of quantum mechanics that aren't accessible to classical computers. These can be broken down into three particular features, which are superposition, interference, and entanglement. And I'll go into a little bit of detail for each one of these and what they mean and how they come into play in the development of quantum algorithms. So ultimately, the motivation for quantum computing in terms of at least physics is often motivated by this famous quote by Richard Feynman, where he pointed out that ultimately nature isn't classical and therefore there's no reason why it should be able to be simulated on a classical computer. So if you really want to get into the details of simulating complex quantum mechanical natural systems, you really need a quantum computer to be able to do that. It's not just that the nature of things that is quantum mechanical. Classical computers have been developed for decades. There's a ton of algorithms that exist for calculating properties of molecules and complicated quantum systems. But you reach a certain point where certain problems or the scale of certain problems simply becomes too large to be able to be handled efficiently by classical computers. And what I mean by efficiently is if you were given an infinite amount of time, 1,000,000 years, for a classical computer to solve a problem, in principle, it will be able to do so. What quantum computing offers is to be able to solve a similar type of problem that would take a classical computer, quote unquote, an infinite amount of time. They'll be able to do it much, much faster. So it becomes much more efficient and much more economical to be able to do certain class of computations once you have a quantum computer. So we'll start from the very beginning, essentially. The basic unit of computation, as you probably all know, in a classical computer, these are bits or binary digits. There are several representations for them. I have here two pictorial cartoons of what a bit could be. It could be something that goes between an on and off state, or often is depicted as the head and tails side of a coin. So anything that can be represented as two discrete states can, in essence, be a bit. I see there's a question. Feel free to unmute yourself and ask your question. Okay. Atasaria, I see your hand is up. Yeah, so as I was saying, a bit is basically anything that can be represented as two discrete states. Ultimately, any classical computation involves the transformation of these bits through a series of logical operations, typically represented by these logical gates, and they come together to build circuits. So any classical computation is a series of bits organized in a circuit that are transformed by a series of logical gates. In contrast, the basic unit of computation of quantum computers are quantum bits, or qubits for short. One of the main differences that's illustrated here is a quantum bit can exist in a superposition of 0 and 1. It's a common misinterpretation to say that it exists simultaneously in both of those states. What it really means is we can't be sure which state exactly it's in up until we measure it. So for our purposes, we say that there's some chance of it being in the state 0 or in, let's say, an off state, if you were to make an analogy with a classical bit, or some probability of it being in the on state or the 1 state. Abstractly, a qubit is sometimes represented as a vector in the sphere called the Bloch sphere. And the main states that are of interest to us are at the poles of the sphere, the 0 state at the North Pole and this 1 state at the South Pole. That being said, it's important to remember that, like classical bits, qubits are ultimately physical entities. They're physical devices or physical things. Here, I'm illustrating two such representations. The one on the top is a superconducting qubit, so something like what you would see companies like IBM and Google developing. The picture at the bottom here, it's also an abstract representation of a qubit. This is something called a GKP state, which is the type of qubit that we're working with at Xanadu. And it's ultimately just the information is encoded in photons. So it remains a physical entity. So a little note on notation. If you've never seen this strange notation before, we typically denote the 0 state of a qubit by the 0 ket. Mathematically, you can represent that because you have essentially a two-dimensional space in which the qubit can exist. We represent that by a 1, 0 vector, and the 1 ket we represent that by the 0, 1 vector or by the 1 ket state. Try to fix this a bit. Okay. Let me just test for volume. Is it better now? You can put in the chat if you want it to be a bit louder. Yeah, good. Okay. Yes. Okay, perfect. Okay. Yeah. So this superposition of the qubits is often represented mathematically by this equation, where you have some combination of 0 and some combination of 1. These two numbers, is alpha and beta, represent probability amplitudes. They're not exactly probabilities, as we'll see in a little bit, but they give you a sense of how likely you are to find the qubit in either one of those states when it comes to actually measuring the state of your qubit. When you have multiple qubits, as you need if you want to do any kind of interesting computation, you end up having to describe this in terms of a more complicated vector, so to speak. So if you take your two qubits, if you look at the top right, represented by these vectors, the mathematical operation that lets you combine the space in which each of those qubits exists is this tensor product, and then you go from being in a two-dimensional space for each qubit to being in a four-dimensional space for two qubits, and in general to a 2 to the n space for n qubits. And here's a representation of if you combine two qubits that are in state 0, we denote that in shorthand by this 0, 0 state. So I mentioned to you that classical computations are ultimately logical operations being done on classical bits, organized in a classical, what I'll call a classical circuit from now on. In quantum computing, it's very analogous. We have these things called quantum circuits. Quantum circuits are representations of qubits, the different qubits that we have. So if you have 3 qubits, this will be represented by 3 horizontal lines. Typically, we represent the initial state of each of our qubits at the beginning. So the bottom picture here shows that they're all starting in this ket 0 state. And when you do a quantum computation, what you're doing is you're applying a series of quantum gates to your qubits. So this is just a cartoon. This isn't what the actual quantum gates look like. But the triangles and the circles here represent single qubit gates. So they only transform a single qubit at a time. And then these longer rectangles are multi-qubit gates. So you can have qubits interact with one another to perform more interesting operations. At the end of the circuit, you see this symbol with a half circle and an arrow. This is a representation of the measurement process. So unlike classical computations where you typically don't have to worry about measuring things, in quantum computing, you have to explicitly take into account the measurement process. When you measure a quantum system, you're destroying the superposition and you only get one of the possible answers, or one of the possible states that it could have been in. So here, the circles here, the triangles, all of these symbols are just cartoons of gates. They don't really represent anything at the moment. I'll show you what the actual gates look like in a little bit. Okay. So the anatomy of any given quantum circuit is broken down in this picture. As I mentioned, the horizontal lines represent the different qubits that you have. The first symbol, all of these ket zeros represent the initial state of your qubits. Typically, you always start a computation with all of your qubits in the 0 state or on some agreed upon initial state. The stuff that you see along the horizontal lines, these are actual quantum gates, the way that we represent actual quantum gates. We'll see some of these in the examples later on, but you have this H1 is called the Hadamard gate that builds an equal superposition of the 0 and 1 state in a given qubit. You have gates that you can see depend on parameters. That's this Rx and Ry gate. This will be important later on when we look at variational circuits, so circuits that depend on parameters that you can vary and optimize to achieve some goal. And then you also have these multi-qubit gates that seem to be linking different qubits together. These are important to create entanglement, which is one of the resources I mentioned that you can tap into for quantum computations. And then the last bit here is this measurement process that we'll spend a little bit of time talking about in case you're not familiar with measurements in quantum mechanics. Okay, so let me just pause here to see if there are any questions so far. Feel free to just type away in the chat. I'll keep an eye on it if you have questions. So measurements in quantum computing are really central to the topic. I'll give you a brief primer on what measurements look like in quantum computing. So just to go back again really quickly, what you're doing here in this given quantum computation running through a circuit is you initialize all of your qubits in a given state. You apply a series of operations. It's similar to doing the logical operations on the bits. You're transforming them in some predefined way, following an algorithm, so that the end result is something, or you're calculating a quantity that you're ultimately interested in. The gates can be single qubit gates, multi-qubit gates, gates that depend on input parameters. So something that you can change as a user in your quantum computer. And then ultimately, you can't fully observe a qubit in a superposition. When you measure a qubit, you are only choosing one of the possible states. So when you have a superposition like this, you can't ever measure both 0 and 1 at the same time. When you do a measurement, you have some chance of finding your qubit in state 0 and some chance of finding your qubit in state 1. So the way that these two states differ from the normal bits is they don't. The difference is these are representations of a quantum system, and you can mix a little bit both of them. So in a classical bit, you can only have 0 and 1. In a quantum bit, you can have some chance of it being in 0, some chance of it being in 1. You don't know which one it is until you actually measure it, so until you look at it. The difference between a cat and a bra is it's not important for us really. It's just mathematically different. You can think of it as the difference between a row vector and a column vector. So it's not so much that bras serve as a qubit, they're just a different mathematical representation. Okay. So when you have a single qubit gate, or a single qubit, sorry, and it exists in some kind of superposition of 0 and 1, sometimes you'll see this in textbooks represented by this weird notation that I have over here. If you don't understand this notation, don't worry about it. It's just to make you a bit familiar with it. When you actually go in to measure your qubit, I mentioned that these coefficients are called probability amplitudes. The square modulus of those probability amplitudes gives you the actual probability of observing a qubit in a given state. So the C0 squared gives you the probability that if you were to make a lot of measurements, let's say 100 measurements, how many times out of those 100 measurements you would expect to measure the qubit in state 0. And likewise, C1 is the probability of measuring your qubit in state 1. If you build this up to now consider 2 qubits, you now have 4 possible states instead of the 2. These are both qubits being in 0, 0. One qubit, well, what I'll call the first qubit being in state 0 and the second qubit being in state 1. You can have the first qubit being in state 1, the second one being in state 0, or both qubits being in state 1. These are all of your possible choices. It's not to say that you're always constructing this kind of state when you have a general 2-qubit system. But this is all of the resources that you have available to you in some sense. In that case, you have different probabilities for measuring your 2-qubit system in any one of these states. So if you want to know the probability of measuring your 2 qubits, one of them in state 0, the other one in state 1, that would be given by the coefficient C01 squared, for example, or C10 squared. And similarly for the other ones. What I would like you to take away from this is you will always have, when you're doing a quantum computation, what you're ultimately interested in is one of these states represents the answer that you want, the answer that you're interested in. That means that there is always some probability of obtaining the wrong answer in a quantum computation. And what you do when you design a quantum algorithm is fundamentally different than what you do with a classical algorithm. A quantum algorithm, you're trying to maximize the probability of getting the state that represents the answer that you want. Okay. So let me try to engage with you a little bit and try to see if you can generalize this to what would be the probability of measuring the first qubit only. Remember, these are 2 separate qubits. They're not necessarily talking to one another. They're not interacting with one another. Instead of measuring both qubits, I want you to think of the thought experiment of just measuring one of the qubits. And you want to find what the probability of measuring that first qubit in state 0 would be based on these previous rules. So I'll give you a few seconds to think about that. And while you think about it, I'll just answer the question in the chat. So classical computers at the moment are actually faster than quantum computers for a variety of reasons. So it's not necessarily, faster in terms of of time. Where a quantum computer will begin to differ is in the efficiency. So each computation might take longer, but you might need to do less computations to reach the answer in a quantum computer compared to a classical computer. Okay. So does anyone have
Yeah,
any ideas?
I do. Yeah. Okay.
Yeah.
I do have a question on
Mhm.
understanding the general qubit systems.
Mhm.
Now this expression the one that you just presented with the wave functions and the coefficients and the like.
Mhm.
The two zeros, is that a Slater determinant? Is that a determinant, or it's actually another notation of the cat? Because if we have two of those zeros, like what is the actual interpretation of that? I'm trying to
Yeah.
figure it out.
Yeah. So the actual interpretation of this, I'll go back here. So remember here, when you have multi-qubit states, you have each qubit is represented by this ket 0 or ket some state. If you have two qubits in state 0, that's what we represent by this 0, 0 state. It means you have, let's say two electrons that they're oriented in the same direction. If you have a 0, 1 state, you have one electron pointing in one direction, the other one pointing in a different direction in terms of its spin. If you're familiar with quantum mechanics, you can think of it as if you have two coins, they're both heads in the 0, 0 state. If you have 0, 1, 1, 0, it will be one is heads, one is tails. If you have them both in 1, 1, then they're both tails. And you have some probability of each of those cases. So here, the 0, 0 state could be you have both coins in heads. 0, 1, 1, 0 is one tail, one heads. 1, 1 is both of them tails. And you're mixing the chances of finding either one of those states. Now, this question is meant to say if you only look at one of those coins, what's the probability of finding it in state 0? And the way we differentiate each one of those qubits is we take the convention that the leftmost number represents the first qubit, the rightmost number will represent the second qubit. So the answer to this is you have to look at the probability, the possible cases in which you get the first qubit in state 0. And the answer to that is that there's two possible ways of doing it. You can either get both qubits in state 0, or the first qubit in state 0, the second qubit in state 1. So you have to add up the probabilities of obtaining those two outcomes. Okay, so those of you that put it on the chat, you got it exactly right. And then typically you can't do very much of interest with just two qubits. So you ultimately generalize this to n qubits. The notation gets complicated, but just to give you an idea of what this will look like. As I mentioned, ultimately what you're doing in quantum computing is you're modifying these probability amplitudes or these coefficients in such a way that you're maximizing the chances of getting the state that you want that represents the answer that you're looking for in your computation. So what that means, one of the reasons why quantum computing, if you compare raw speed, is sometimes slower than classical computing, is because you have to run a circuit several times over. Each time you're doing a measurement, you're obtaining some value. They need to run it over and over again until you get an average value of whatever you're trying to observe. Okay, so typically you need to run a computation hundreds or thousands of times to be able to get a good estimate of the answer that you want, because sometimes you're going to get the wrong answer, sometimes you're going to get the right answer. And if you design your algorithm correctly, you're getting the right answer most of the time, but you still need to measure several times. You need to do your computation several times to measure the outcome. Okay. To give you an example, if you've never heard of this algorithm, don't worry about it. This is just a a histogram representation of the outcome of a quantum computation in something called quantum phase estimation, which is an algorithm essentially for estimating eigenvalues. You can see that it's estimating something called the phase, ultimately, which is a number. What you see here represented is the answer that we wanted is this 0.001. And you can see because we designed this algorithm correctly, we have a really high probability of obtaining that measurement in our computation. But every now and then you get the wrong answer. You get values that are incorrect in your computation. But you've minimized that so much that after you've run several measurements, you can pick out the answer that happened the most often, which, if you've done things correctly, is the correct answer to your problem. So I mentioned that there's 3 resources that don't exist in classical computing that quantum computers and quantum algorithms take advantage of. That's superposition, interference, and entanglement. And what you're doing with each one of those, remember, is modifying the chances of getting the state that you're interested in that represents your correct answer. We've seen that quantum mechanics is fundamentally probabilistic. When you measure a qubit, you have a chance of obtaining a given outcome to your measurement. But it's, if all there was to quantum computing is that it's probabilistic, you actually wouldn't gain anything. You wouldn't have any extra potential for speedups in computations or for efficiency. An extra resource that quantum systems have over classical systems or over probabilistic systems is this phenomenon of interference. And this is often depicted by this double slit experiment where if you send a bunch of particles, what you would expect is a collection of particles at the location of the 2 slits, if you were to look at them in some screen later on. What you actually observe is this kind of interference pattern, almost as if the particles were going through each slit simultaneously and interfering with one another, as you would see in waves, for example. Okay, so any quantum algorithm is going to take advantage of this interference phenomenon. It's going to modify the system in such a way that it'll interfere so as to maximize the probability of observing something. So yes, it essentially means that classical computers have an accuracy probability of 1 for all intents and purposes. When you do a computation, if the computer is designed properly, you're not going to get the wrong result unless you did something wrong yourself. So we've seen superposition and interference. You need superposition to be able to get interference. However, if you stop and think about it, you'll notice that superposition by itself is not enough to get an exponential speed up in computations. The reason for that is, remember, we had 2 numbers to represent the state of a single qubit. If you have n qubits, you will need 2 times n numbers to fully represent the state, and that's not a very strong increase in resources. The other property that comes into play is called entanglement, which it's difficult to understand because there's no real classical analog to entanglement. But one example or one representation of that is a story of a mathematician called Bertelmann, Mr. Bertelmann. He apparently used to always wear 2 different colored socks. To go along with the cartoon here, we'll say that one sock was blue, the other was red. If you were to observe only one of Mr. Bertelmann's socks, you would immediately be able to tell me what the color of the other sock is, because their colors are correlated. You always know that it's one blue and one red sock. So if you were to see the blue sock, even though you haven't seen the red sock, you will be able to say right away the other sock must be red, because I know the correlation that exists between Mr. Bertelmann's socks. This type of correlation between qubits results in this exponential increase in the resources or in the numbers that you can represent abstractly in an n qubit system. Now, instead of needing 2 times n numbers to fully specify the state, you would in principle need 2 to the power n numbers to fully specify the state. What that means is that if you only have 100 entangled qubits, you would now in principle have access to 10 to the 30 numbers to be able to fully specify the state. Now, I want you to put this in contrast with a normal computer. A classical computer with 100 bits, you can't do very much with that nowadays. But a quantum computer with 100 entangled qubits, you already have more raw computational power than any classical computer that exists today. It's 10 to the 30. 10 to the 30 is an estimate of 2 to the power of 100. So this should really be 2 to the power of 100, which is approximately 10 to the power of 30. Okay, so this was a very quick introduction to what quantum computing is, what the basics of quantum computing are. What I want to get to now is how do you start playing around with quantum computers and quantum computations. And one of the softwares that we develop at Xanadu is called PennyLane, which is a Python-based open source library made for what's called differentiable programming of quantum computers. So with it being Python-based, it's of course open source. It's easy to pick up. Most people nowadays know Python. It acts as both, I will say, as a simulator of quantum computation. So you try to mimic quantum computations just by simulating it on a classical computer. This comes down to just basically doing linear algebra on your laptop if you're doing simulations. But you can, as I'll talk about later, you can also use it to connect to real quantum computers that are available on the cloud and actually run some of these computations. It's also differentiable, which means that it interfaces very nicely with existing machine learning libraries like TensorFlow, PyTorch, JAX. When it comes to, for example, optimizing a quantum circuit, you can do it very much as you would with a neural network by calculating gradients. And it's also modular, which means that we try to make PennyLane so as to build building blocks for users to put together and generalize in whatever way they need. So rather than providing black box functions that you have very little control over and it's hard to connect them, we have modularity built into PennyLane. See a question in the chat. Yeah, you can estimate the dimensions when you take a tensor product of different tensors, like this generally. The easiest one is if you take tensor products of vectors of 2 by 1 vectors, you'll always have 2 to the power n by 1 vector. So it scales, the size scales exponentially. Okay. So PennyLane is built around a very strong open source community. PennyLane is about 5 years old, and we now have over 50,000 downloads. Where we've released 37 versions of PennyLane. We're in version 0.37 now. We've helped professors integrate PennyLane into over 90 universities around the world. And you can see that it's grown very quickly over the span of 5 years, which is really very important to us because this was the original vision for PennyLane, to really keep our users in mind, make a tool that's easy and flexible to learn and to use, that provides building blocks, and that it has a lot of educational resources for newcomers to the field, like a lot of you, and to be able to integrate it into university curricula and help universities get up to speed in the quantum computing industry. So PennyLane by now has grown a lot. I'll say this list is no longer, everyone describes a small set of what PennyLane is capable of. But you can do automatic iteration of circuits. This is important because if you think of what you need to train a neural network, you need something called backpropagation. Backpropagation is not possible to do on a real quantum computer, so you need new rules for taking derivatives or calculating gradients on a quantum computer, and PennyLane is built centrally around that capability. It has a bunch of different templates and interfaces with both different libraries and different hardware that I'll talk about next. So I mentioned that PennyLane can act both as a simulator and a library to connect to other hardware. We have a range of simulators available. The one we'll use today is this default qubit that you see in the top left. This is just a basic simulator that you can get up to about a dozen qubits, or mimicking a dozen qubits, which is really 2 to the 12 bits, and simulate quantum computations in designing a circuit. If you want to look at what happens when you have noise, then we have a simulator for that. The lightning devices down here, these are more high-performance computing simulators. So all of these are simulators with a C++ backend. So the basic lightning qubit lets you run things a little bit more efficiently on just a regular laptop. If you want to start taking advantage of something like GPUs, then the Lightning GPU and Lightning Cocos devices, if you run with a Linux computer, can also be useful for that. The GPU devices really let you go from simulating about a dozen qubits to simulating somewhere in the range of 25 qubits on a computer with GPU assistance. So one of the strengths of PennyLane is also this device independence. It's both hardware and framework agnostic. You can use PennyLane to connect to different hardware providers. So we don't just want you to use PennyLane to interface with Xanadu's hardware. Right now we have plugins available that let you connect to IBM's hardware, IonQ's hardware, AWS, so long as you have an account with them. It doesn't provide a backdoor to any of these providers. If you have an IBM account, you can interface with our hardware directly with PennyLane. If you're paying for AWS usage, you can do that directly. You can interface with the different hardware they have accessible with PennyLane. And you can also combine your computations with popular machine learning libraries, like I mentioned earlier, TensorFlow, PyTorch, JAX, and so on. So we're getting to the stage of the interactive part of this talk. And what I want you to keep in mind as we go through these examples is, what do quantum circuits look like in PennyLane? Remember, PennyLane is a Python-based library. So a given quantum circuit is going to be represented by a Python function. The order in which the gates appear in your Python function is the order in which they're acting on a given qubit. And you'll see what I mean by that when we start doing the example. And as I mentioned earlier, any quantum computation has to end some kind of measurement. Typically, it's expectation values of some physical quantity we want to measure. For today, we're largely going to look at probabilities. So you take a whole bunch of measurements, you calculate the ratio of observing one outcome over the total number of measurements that you took. And that's the return value of your circuit, of your function that's representing the circuit. The last thing I'll mention before getting into the first example is I mentioned we have different devices. This can represent the simulators that I talked about, or it can represent given hardware that you've connected to. And you have quantum functions representing your circuits. In PennyLane, we have a quantity that connects the device and the quantum function, or a quantum circuit, together. These are called QNodes. QNodes are your basic unit of computation, or basically basic unit of computation in PennyLane. that connects your everything within the QNode is all of the quantum computation stuff that's happening, and everything external to it are classical quantities. So you can feed your QNode with input data. You can send the parameters for gates that depend on parameters, do your quantum computations within the QNode, and then output some kind of measurement, which is now representing a classical quantity. Okay, so what a typical PennyLane or a very simple PennyLane program looks like is something like this. And we'll go through an example shortly, so you don't worry about the details of this. The first thing we typically do is define a device. So we choose whether we want to run things on a simulator or whether we want to connect to hardware. You have a quantum node that is decorating your Python function that's representing the circuit. You can see here you have different gates acting on the qubit that depend on parameters that we're feeding into the circuit. And it's returning some kind of expectation value of an observable that we're interested in. If we have time towards the end, we'll see an example of a quantum machine learning application where you're going to integrate your quantum computation with classical computations. So in this case, it will be calculating some kind of cost function and gradient. Okay. Again, this is a lot of information. We'll go through it in the examples that follow, and hopefully it'll make more sense. So the first example that I have for you is we're going to build a 2-qubit circuit that starts with both qubits in the state 0, and we're going to build this state. What we're going to return at the end is the probability of observing each state in our 2-qubit system, and the idea is that it'll help you understand what the format of the output in PennyLane looks like, and to interpret the result and be able to say whether you successfully created this state or not. What this state here represents, remember, is you start with both qubits in the 0 state. You're going to build a superposition where you have 50% chance of both qubits still being in the 0 state, or both qubits now being in the 1 state each. If you compare this to the previous 2-qubit state that I showed you earlier, you'll notice that there's no chance of getting the qubits in 2 different states. So you can't have one qubit in 0, the other one in 1. It's either they're both in the 0 state or they're both in the 1 state. So just see something. Are you able to see, do you still see the slides, or do you see something that looks like a notebook in the screenshot right now? A notebook, okay, perfect. So what I invite you to do is open up a Google Colab session. You might see something that looks like this. You'll get a pop-up box, and what I want you to do is click New Notebook. Okay, and then you should see something that looks like this, and we're going to gradually fill in each one of these cells. So once you have a Google Colab notebook open, the first thing I want you to type is this !pip install PennyLane. You can either click on this play button to run it, or if you're on a PC, you can click Control Enter. And then just, if you get this pop-up, just say run anyways. If you're on a Mac, by any chance, then it will be Command Enter. You can also use, well, if you use Anaconda, you need to have PennyLane locally installed. I believe Henry shared instructions on how to do that, but if you haven't done that, then the Google Colab is really the fastest way so that you don't have to install PennyLane locally on your computer. So if everything worked out for you, you should see this list of things coming down. This is just installing PennyLane on Google's servers for the duration of our session.
Please, what did you click next after typing in the PennyLane?
You can click on this play button.
Oh, okay.
You can also click Control Enter as a shortcut. The next thing I want you to do is import PennyLane. So we've installed it. Now we need to import it into our notebook. For historical reasons, the shorthand we use for PennyLane is QML. And it's just that we don't have to type out PennyLane dot something whenever we want to call a function. And then we also are going to need NumPy, but we're going to need a special version of NumPy that's built into PennyLane. So within PennyLane, so from PennyLane, we're going to import NumPy, and we're going to call that PNP for shorthand. And just run it, and I see a hand up. If you have a question, you can unmute yourself. Akawa, if I pronounce your name correctly.
Yeah, I was the one who asked about the where to click next.
Okay,
Yeah.
perfect.
Oh, also after that, the import. Where do you go to next after clicking after everything comes down? After you click the play, and then
so
the everything. Where do you click next? To type to import.
You should be able to in this cell. You can there should be something like this that comes up that you can add an extra code cell. Yeah.
Okay.
Yeah, exactly. Insert new code cell.
Okay, thank you.
No problem. So what we want to do then is remember the first step is you want to create a device. You want to choose what device you use. In this case, we're just going to use the default qubit simulator. The way you do that. So we'll call it dev. From PennyLane, we'll call our device function, and we're going to tell it we want to use the default qubit simulator. And in PennyLane, qubits are represented by wires. So if we want to specify that this device is going to have 2 qubits, we say it's going to have 2 wires.
Underlined red, and I don't understand.
Yes. So if you open the new Google Colab session, first thing you want to do is pip install PennyLane, and then you can run that. If you're running on Google Colab, it shouldn't, if it's not able to find the PennyLane module, it's either that you haven't installed it or that you haven't imported PennyLane. So once you pip install PennyLane, you go here and click code. This is where you can import PennyLane. And then later on, we'll also need NumPy, so we can say from PennyLane import NumPy as PMP. And then add an extra, run that, and then run it, get an extra code cell. And this is where you have the QML, this is where you define the device. Oops. Okay. And then it's going to progress in a similar way. When you want to get an extra code cell.
Sorry.
Yes.
Can you just explain this line that you just wrote? What does that mean?
Which line?
This line that you just wrote. Yes,
This one?
yes, yes.
So this is a device in PennyLane that specifies whether we want to use a simulator or whether we want to connect to a quantum computer available on the cloud.
Okay.
We're going to connect to a simulator that's built into PennyLane.
Okay.
Those simulators are devices. So we're saying from PennyLane, I want to define a device.
Okay.
That device is going to be default.qubit, which is just a basic simulator.
Okay.
And we want this device to represent 2 qubits. In PennyLane, qubits are represented by wires. So we say wires equals 2 to tell PennyLane I want to build a device that's going to have 2 qubits.
Okay.
Okay, so let me go back to this one. Okay. So what we want to do now is construct a QNode that's going to link the device to our quantum function. I mentioned that a QNode, the way you type it is like this. So you have this at symbol QML.QNode. This is saying construct the QNode that's going to link the device that we defined in this line 3, this one, to the function that I'm about to define right at the bottom. So we define a circuit as a Python function. We're going to call that circuit. To begin, our circuit isn't going to have any inputs. So we leave the inputs empty. And the 2 gates that we need to build that state that I mentioned is we first need to apply what's called the Hadamard gate to the first qubit. What the Hadamard gate is going to do is it's going to take a qubit in state 0 and it's going to make an equal superposition of that qubit in state 0 and 1. And then this wire 0 is telling PennyLane, I want to apply this Hadamard gate to the first qubit. And then the next operation that we want to do is something called the control NOT gate, which in PennyLane is called the CNOT. This gate it involves 2 qubits. One of them is called the control qubit, and the other one is called the target qubit. What a CNOT does is based on the... Yes, sorry.
Sorry, I got to lost a bit with the @ and the PennyLane.q node. Can you please re-explain that?
Yeah, so
with the @
this @ is not important. This is something in Python called a decorator. What a decorator is it's not so much what a decorator is in Python, it's telling PennyLane, I want you to build a QNode that connects this device or our simulator to this circuit that we're building here. So if you go back to the presentation here, what we're saying is we have a device, we have this default qubit device, we have a circuit that we're defining that represents, or a function that we're defining that represents a circuit, and we're connecting them using this QNode to build one unit of computation that we're going to do all of the quantum stuff in. And that's what this represents is we have a device, we have a circuit, we want to link the two with this QNode. So the circuit that we're building here is this Hadamard is taking a single qubit in a given state, and it's building an equal superposition. So it's making it equally likely to find that qubit in state 0 or in state 1. That's important because remember, superposition is one of the resources that you can use in quantum computations. So we don't want to just have everything in state 0 because then we're not gaining anything. We're not using any quantum mechanical properties. The Hadamard gate starts to tap into this first one of superposition and interference ultimately. This CNOT gate, I was saying, takes a target qubit and, a control qubit and a target qubit. The way we're going to write that is like this. So wires, square brackets 0 and 1. The syntax here is this, the first one is representing your control qubit. The second one is representing the target qubit. What a CNOT gate does is, depending on the state of that first qubit, it may or may not apply an operation to the second qubit. Okay, and I'll explain what that looks like in a moment once we visualize the circuit. And then what we want to return ultimately is the probability of observing all the possible states that we have in our 2-qubit system. Okay, so when you're ready, you can play that cell. So to explain what the CNOT gate does, I'm going to draw what the circuit we just built looks like. The way we do is with this MPL function. We give it as input the name of our function. We called it circuit. This is an optional argument. You can also tell it I want it drawn in the style of PennyLane. And this is what a pictorial representation of a circuit looks like. So you can see we have 2 qubits. We first apply a Hadamard gate to the first qubit. And then this control NOT gate is one of the ones that I showed you earlier. It says essentially if the first qubit is in state 0, don't do anything to qubit 1. If the first qubit is in state 1, apply a flip operation to the second qubit. A flip operation means if the second qubit is in state 0, flip it to a state 1. If it's in state 1, flip it to a state 0. So what this is doing, in essence, is building a correlation between your 2 qubits. The state of the second qubit after the CNOT gate is going to depend on the state of the first qubit. Okay, so here we're tapping into entanglement a little bit. And then we finish the computation with a measurement process. So we can run this circuit. And remember, when we run the circuit, what we're doing is performing these operations and outputting the probability. The output that you see is this vector, essentially. Don't worry about the tensor part. that says 0.5, 0, 0, and 0.5. So given that the state that we wanted to build was this one, how do you know if what the state that we've constructed is the correct one? I'll go back here to make sure everyone is following. So when you type in the gate names, it's important that you stick to the correct syntax. If you, for example, if you type Hadamard with a lowercase h, it's going to give you an error. It needs to be with a capital H. Likewise, C0 has to be all in capital letters. When you draw your circuit, you need to include this extra parentheses, these ones at the end, because it's going to be expecting input parameters to the gates. It doesn't know that the gates don't take any parameters, that the circuit doesn't take any parameters, so you just leave this parentheses empty.
After draw your circuit, is there any code below draw your circuit, or we were just taking this code where we are just drawing the circuit? Just above, above, yeah, like where it says show your code, there's nothing there, right?
No, there's nothing there.
Okay, thank you.
Okay, so the output of our circuit, remember, is representing probabilities, and we get 0.5, 0, 0, and 0.5. So the reason we return probabilities is we need to return something that is classically observable. We're not returning the device. The device is just an abstract simulator. It doesn't represent anything physical, really. We were interested in calculating the probabilities of observing the different states of our qubits, because there's two. Remember, whatever you return has to be something classical. It's either an average value of something, a probability of something. So the interpretation of this is, remember, when you have a 2-qubit system, you have 4 possible states. You have the 0, 0 state, the 0, 1 state, the 1, 0 state, or the 1, 1 state. What this is telling you is you have 50% chance of measuring your 2 qubits both in the 0 state. So this will be the 0, 0 state. You have no chance of measuring them in different states. So no chance of seeing one in 0, the other one in 1, or vice versa. And you have 50% chance of seeing both qubits in state 1. And this is exactly the state that we wanted. We wanted 50% chance of seeing the 0, 0 state. Remember, it's the square modulus of this, and 50% chance of both of them being in the 1 state. So to answer Joshua's question, this circuit is exactly building a Bell state. So this is one of the Bell states for a 2-qubit system. There's four Bell states in a 2-qubit system. So I guess some of you might know Bell states represent something called maximally entangled states. There are four Bell states. What I want you to think about now to help you maybe understand a little bit this idea of entanglement is I want you to consider these two 2-qubit states. The first one is 50% chance of both qubits being in state 0 and 50% chance of the first one being in state 0, the second one being in state 1. And the second state is the one that we just built. So it's this Bell state where you have 50% chance of observing both qubits in the same state. So for each of these cases, what I want you to think about is the possible outcomes and associated probabilities of those outcomes of measuring the state of only the first qubit. So what are the possible outcomes of the first qubit, and what's the probability of each of those outcomes? And if we measure the state of the first qubit, do we learn anything about the state of the second qubit that we have not observed?
Please, I have a question.
Yeah.
Is the amplitude. So what if the amplitude is, let's say, 1 over square root of 3? Because I thought maybe while we were writing the code, we will code something which is similar to maybe 1 over root 2. But I didn't see anything like that. But however, we had the probabilities correct. So how did that happen?
Yeah, so that happened with the Hadamard gate. Remember, the Hadamard gate builds an equal superposition of the two states in a single qubit. So this Hadamard gate is taking ket 0 and it's transforming it into 1 over square root ket 0 plus 1 over square root ket 1. So the Hadamard gate is the one that's bringing in this 1 over square root of 2. Okay, so type in the chat whenever you're ready what you think the solution to this exercise is. Let's say we'll call the state on the left state 1 and the state on the right state 2.
I have a question on 1 over root 2. Is that, are those normalized?
Yes, this is normalized because you have two possible outcomes, each one of them with probability of half. So if you sum up the probability of all outcomes, it adds up to 1. That's the reason why you can't have, for example, 1 over square root of 3. Then it wouldn't be normalized. You would need something like 1 over square root of 3 in one and square root of 2 over 3 in the other, for example.
Thank you.
So, any guesses on this exercise? You can type in the chat if you have an idea. Yeah, so Prince, you have the right idea. For the first one, we'll always find the first qubit in state 0. And then for state 2, you have 50% chance of finding the first qubit in state 0 and 50% chance of finding the first qubit in state 1. Now, the next part of the question is, do you learn anything about the second qubit based on the outcome of measuring the first qubit? For which case? For the one on the left or the one on the right? Yeah, that's right. So the one on the right, it's an entangled state because by measuring the first qubit, you're learning something about the state of the second qubit without having to observe it. If you measure the first qubit in state 0, you automatically know that the other qubit has to be in state 0 as well. If you measure the first qubit in state 1, you automatically know the other qubit is also in state 1. In contrast, the state on the left, you will always measure the first qubit to be in state 0, and you don't learn anything whatsoever about the state of the second one. It could be either in state 0 or in state 1. So the Bell state is entangled because it has this property. The other state, the one on the left, is not entangled. Okay, so for the next example that we're going to do, we're going to need something called the rotation gates, single qubit rotation gates. In principle, there's 3 different rotation gates, each one representing a rotation or about a different axis in this block sphere that I showed you earlier. The Rx gate is going to rotate your vector in this block sphere about the x-axis by some given angle. The Ry gate does the same thing, but about the y-axis, so rotation about the y-axis, and then Rz is the rotation about the z-axis in the block sphere. And this is meant to represent any operation that you do on your qubit. You can always represent your qubit in this block sphere, and operations are rotations around this block sphere. The most general rotation you can have is represented over here. You can combine two RZ rotations and an RY rotation to get any rotation whatsoever that you would like to implement on your qubit. Okay. So we're going to use some of these rotation gates. If you would like, we're not going to do this one together, but if you can take a screenshot of this slide, and I want you to try to build this circuit on your own afterwards. Okay, so it's going to be a 3-qubit circuit using this default qubit device. You're going to apply a Hadamard gate to the first and second qubit, and then an RX gate with a rotation angle of 0.5 to the third qubit. Then you're going to apply 2 more rotations to the first and second qubit, and then you're going to apply a control NOT gate with a control qubit in the first one and a target qubit in the third one, and then end the circuit with a measurement outputting the probabilities of observing the different states. And what you should observe is 8 possible states, because you now have a 3-qubit system. And then when you do this, or if you do this, I want you to interpret what the output is, what the probabilities are telling you about the outcome of your computation. Okay, again, we won't do this one together, but I invite you to try it for yourself later on. So I've given you so far a quick overview of quantum computing. I gave you an example of how you can go about simulating quantum computations with PennyLane. One of the areas of application that's being explored right now is something called quantum machine learning. And at the base of that is variational circuits. So we'll see a quick overview of what that is, and then I'll give you an example on PennyLane of doing a variational circuit application. So ultimately, most quantum machine learning models are represented by quantum circuits that depend on parameters that you can vary. Typically, in analogy with machine learning, you want to minimize a given cost function or a given outcome that you want to optimize for. Quantum machine learning, by and large, has similar applications to machine learning. You can classify data points, you can do regression, you can do neural networks. It's not to say that all of those applications are useful applications of quantum machine learning. It's something that's being explored right now. But in principle, you could do something like that. So the algorithm that we're going to follow is we're going to construct a circuit that depends on some parameters. We're going to construct a cost function that represents an objective that we want to optimize for. And we want to minimize that cost function by computing gradients and optimizing the parameters in our circuit. Did you want me to go back to this slide? Okay, so a variational circuit and a variational algorithm has 3 main ingredients. It has a circuit, what we call a circuit ansatz. What a circuit ansatz is a guess of what the function looks like. And I'll explain what I mean by that when we do the example. It has a problem-specific cost function. So every problem you want to do with a variational circuit will have a different objective. You need to encode that objective into a cost function. And then we also need a training procedure that will optimize the parameters in the variational circuit to fulfill our objective or to minimize the cost function. These variational algorithms are an example of what's called hybrid computation. Hybrid computation is something that is popular currently in the industry, partially because real quantum computers have limited resources, and they suffer from a great deal of noise. So you don't have access to very many qubits in a quantum computer, and those qubits are subject to noise and mistakes, essentially. So what people started doing is they performed part of the computation on the resources available on a quantum computer, and they did most of the computation on a classical computer. And they will combine those two resources to do something useful, or in this case, to optimize the parameters in a variational circuit. And it's something that's historically been of interest in the last few years in quantum computing because of limited resources, but it is the direction that the industry will likely take for a while, simply because classical computers have had decades of development, and there's very powerful classical algorithms that work very well for certain tasks. Those algorithms might perform better, or there might not exist a quantum analog to be able to run that on a quantum computer. So classical computers will still have a big role to play in the future of quantum computing. But as the resources that we have available in terms of qubits that don't suffer from noise, we'll be able to do more and more quantum computations and then find the balance between the two to perform useful applications of quantum computing. This is the example we're going to go through right now. Is a very simple one. It's not maybe a particularly interesting one. There's no application of it, but it's just to give you an idea of this type of hybrid computation. So what we're going to do then is what I call a toy example of quantum machine learning. What we have in this example is we're going to have 10 data points between 0 and 2 pi that we know are modeled by a sine function. So it's going to have this sinusoidal pattern. What we want to do is build a quantum circuit that's going to, we're going to build a quantum circuit to do nonlinear regression on this data. So we want a quantum circuit to fit the sinusoidal function to the data that we give it. Once we do that, we're going to have a set of training data. We're going to give the circuit data that it hasn't seen before, that is still coming from the sine function. And we're going to ask it to predict what the values of the sine function are for those values for the data that we're going to feed it. And we're going to see if it's able to predict the correct values. So this one is going to go a little bit faster, but just bear with me. So we're going to need to generate some plots. So we're going to import matplotlib.pyplot as usual as PLT and run this up. Now we're going to generate the data, the 10 data points between 0 and 2 pi that come from a sine function. So we're going to need numpy linspace. Okay, so this is going to be our training data. So we're taking 10 data points equally spaced between 0 and 2 pi. These I mentioned are modeled by a sine function. So our data is ultimately going to be the values of the sine function at these data points that we produced here. And then here we're going to generate the test data that we're going to use afterwards. So we need an extra set of data points. We want these to be different than the training ones. So instead of starting from 0, we're going to start at 0.2. And we want 10 of these. So what we're generating here is 10 data points that are shifted from our training data by a factor of 0.2. And then this is the labels of our test data. And that's okay, so this is our training data. You can see it follows the sinusoidal pattern. We have 10 points scattered between 0 and 2 pi. And then look at the same. And so the blue dots represent our training data. The orange dots represent our test data. You can see the difference. This is what we're going to train the circuit on, the blue ones. The orange ones are the ones that we're going to test the circuit with. So now we go back to what we did before. We need to create a device, create a function representing the circuit, and link the two with a QNode. So this part is the same. We're going to stick to our default qubit simulator. And we're only going to need a single qubit for this example. So we're going to say wires equals 1. Now, to create our circuit, we're going to create this circuit ansatz that I mentioned earlier. This is a guess, usually an educated guess, of what could represent our function that we're trying to model. What we're going to do, the first step of most quantum machine learning algorithms is to encode the classical data into the quantum circuit or into the state of the qubit. The way we're going to do that is with one of these RX gates. So to our circuit, we're going to feed it one of our points, one of our blue points here. And we're going to encode the value of that point into a rotation. So if we give it a value of 0, that means no rotation about the x-axis. If we give it a value of pi, that means a rotation of pi about the x-axis, and so on. So the first thing we want to do is some way of representing what the classical data looks like in terms of the state of the qubit. After that, the two gates that are going to depend on parameters are going to be an RY and an RX gate. These parameters are the ones that we're going to vary or optimize to try to make the circuit learn that the data is coming from a sinusoidal function. And then I didn't talk very much about this, but we're going, instead of returning probabilities, we're going to return the expectation value of a measurement. What a measurement along the z-axis is a measurement that has as outcome either 0 or 1 in terms of the single qubit.
Oh, can you please go back to your where you were drawing the graph upside there? I didn't get the code exactly.
This one?
Yes, this one there. Okay, that there.
Yeah.
Okay, let me just take a screenshot. Okay, thank you.
No problem. Okay.
Sorry, can you go back there? I want to take the screenshot of that.
This?
Yes. Okay, thank you.
Okay. So if everyone is ready, we're going to build our QNode, attach the device to that QNode, define our new quantum circuit that's going to serve as a variational circuit. This is going to take as input one of the data points from our training data set, and it's going to take two parameters, one for the RY gate and one for the second RX gate. So the first gate that we apply is this encoding RX rotation that is representing the value of the classical data in the state of the qubit. So the qubit starts pointing it towards the north pole of the block sphere. If we have any kind of rotation, it's going to gradually shift the state of that qubit along the x-axis. And yeah, I can share the notebook, the completed notebook afterwards. So if there's something that you miss, you'll have access to it afterwards. The next part is going to be our ansatz. So that's this RY and RX rotations. Oops. So the first one is an RY rotation that's going to take one of the parameters in this variable. The second one is the RX rotation that's going to take a second parameter and again apply it to the first qubit because we only have a single qubit circuit. And then we're going to return an expectation value. We do that with X file. And the way that we do a measurement with respect to the z-axis is with this qml.polyz of the first qubit. Remember, all this means is that the possible outcomes that you have is either 0 or 1, with different probabilities depending on how you've modified the state of your qubit. All right, so again, you're gonna have, I'll share the completed notebook with you afterwards, so you'll have access to it if you miss anything. Just to make sure that we've done this correctly, we can once again draw our circuit. Now we want to draw the circuit which is defined, which we call quantum circuit. For fun, we want to do this in the style of PennyLane, but you don't have to type that. Here, our quantum circuit now takes input parameters. So we need to specify that. So we're going to say, this is more or less random when you do the drawing, but we're going to say a data point of 0.1 and the two angles of rotation that act as the parameters for our Y and our X is 0.2 and 0.3. And which part did I miss? Oh, I didn't run this. Okay. So you can see here, we've created our circuit successfully. We have a 1 qubit circuit. We're encoding the data point in this RX rotation. And then we have an RY and an RX rotation serving as our ansatz or as our guess for what the function will be represented as in our circuit. And then we end with a measurement at the end of the circuit. So this next part we're going to do the classical processing. So what we've done up until this point, it's all the stuff that happens in the QNode. It's all, or if you were to do this on an actual quantum computer, it's all the part that will be done on a quantum computer. The next part will be the part that you would do on a classical computer, which is the optimization part of the computation, simply because classical computers right now are better at doing that than quantum computers. So the classical pre and post processing that we're going to do is we need a way of comparing the output of our circuit to the output that we expect. So we know the answer that we should get, the circuit doesn't know that. So we need a way of capturing the difference between the output of the circuit and the value that we expect. Maybe just checking in. Is everyone still able to see the screen? Okay.
Yes.
So to capture that difference, we're going to define a loss function with the predictions from our quantum circuit and the value that we expect to get from our sinusoidal model. To begin, we have no loss. We don't know what the loss is. We just initiate that. We want to go through all of the target values that we have. The labels associated with those targets are the indices of the array targets. The prediction of our quantum circuit is going to be the associated value of the array predictions. And then the loss function that we're going to use in this example is the square difference between the prediction and the target label. And then for each one of those points, we're going to add the loss to the total loss. At the end of it, we're going to return the total loss. So what we're doing is we're going through each target, we're comparing the square difference between the target and the predictions, and adding up all of those square differences to compute a total loss value. This total loss value represents the difference or the discrepancy between what the circuit is outputting and what you would like it to output. Now, I said that one of the ingredients of these variational algorithms is a cost function. So we want to define what that looks like now. This cost function is going to take some of the parameters of the circuit, and it's going to take the data points and the label of those data points. That's what we have called X and Y. The predictions here are the outputs of our quantum circuit. So we're taking all of the data points that we have, we're calculating the prediction from a quantum circuit and putting that into an array. And then we want to compute the cost function as the total loss function between the predicted values and our expected values. And return that the value of the cost. Okay, so the next step, we've set up all the processing that we need of the data. What we want to do now is choose an optimizer. Typically, that's something like gradient descent, but there's other optimizers you can choose. Guess an initial set of parameters. We need something to start the circuit with. And then we're going to optimize it. So we're going to vary the parameters by optimizing them with gradient descent until we minimize the value of our cost or of our loss function. In the interest of time, I'm going to go a little bit faster on this, but again, you're going to get the notebook afterwards. So we choose the gradient descent optimizer. As I said, there's other ones that you can choose from. This is just the most basic one. We're going to take a step size of 0.3. You can also vary that. Typically in a machine learning framework, the step size is one of the parameters that you need to optimize. We're going to guess an initial set of parameters for our circuit. This can be literally any value that you want. We're going to just guess 0.1 and 0.1. And one of the main differences between regular NumPy and PennyLane's version of NumPy that we're using is you need to make the arrays differentiable. And regular NumPy did not do that before. So we have a special version of NumPy within PennyLane that allows us to make the arrays differentiable by specifying this requires grad equals true. In contrast, we don't want our data to be differentiable. So we're going to say that for training data, we don't want that to be differentiable. So we say requires grad is false. Whenever you do an optimization, you have two choices. You can either run it for a certain number of iterations, or you can define a certain tolerance, which is if after an optimization step, the difference in your loss function is less than a certain amount, you can stop the optimization. We're going to first define a maximum number of iterations in case something happens, the computation won't run indefinitely. And we're going to define an optimization routine with a maximum number of iterations. The optimizer that we define, our cost function, the parameters in our circuit, and our data set. So we want to iterate over the number of iterations that we specified. At each step, we want to save the value of params. There's going to be two other outputs to our optimization that we're not interested in. And then we're going to record the previous value of the cost function because we want to make sure that that cost function is decreasing as we run our optimization routine. If it's not decreasing, it's usually a sign of something having gone wrong. So we define within our optimization routine, we call the step and cost function that will run a step of optimization and recompute the new cost function. We need to feed it the cost function that we defined before, the parameters, and the data set. And then it's almost done. There's maybe like 10 minutes left. So we return params. And then just to show you the end result, you can plug the results. So here, what this is showing is the training data set that we had that I showed you earlier, the test labels, which are the ones that are shifted slightly, and the predictions of our circuit to the test labels. And you can see that with our optimization routine, we trained the circuit on the blue squares, and we asked it to predict the value of the red circles. Here, the black X's represent those predictions, and you can see that they line up very well. So long story short, we were able to train this single qubit circuit to fit sinusoidal data to our model. Okay. So again, the second part was very fast. So you're going to have access to the notebook and you'll be able to review the code afterwards. So shifting gears to sort of conclude the presentation. The expectation for this isn't for you to, be able to do quantum computing tomorrow. It's really to give you a taste of what the field is about, where you can go afterwards. So I mentioned that one of the central features of PennyLane is that we focus a lot on educational material. We have over 120 different demos that you can explore. The demos are typically somewhat advanced, but you're welcome to explore them. They're interactive tutorials of PennyLane implementations of a given topic. If you want additional practice problems, we also have PennyLane challenges. If you open a PennyLane account, you can try out different programming problems associated with different topics. The main resource that may be of interest to most of you is the Quantum Code book. This is an ebook that is accessible on PennyLane.ai. All you need is a PennyLane account, and it takes you through an introduction of quantum computing, starting from the very basics, starting from what are qubits, how to build circuits and gates in PennyLane, and a variety of introductory algorithms. So I really encourage you to explore the Quantum Code book if you're interested in learning more about quantum computing. So from here, again, I really encourage you to check out PennyLane.ai further, explore the resources that we have. We also have a discussion forum that we monitor quite closely. In the discussion forum, you can ask technical questions if you're having trouble doing something in PennyLane, if you're running into problems in the codebook or the demos. You can connect with our experts that will help you with your questions. If you want to keep up to date with what we're doing at Xanadu, we have a newsletter that you can subscribe to if you follow this QR code that's here. We're also on social media, so you can follow us on LinkedIn and on Twitter or X. We typically make announcements on new features that we released, new things that we're working on. So it's a good way of keeping in touch with us. And finally, if you have further questions, you can always reach out to me. My email is down here. And with that, I'd like to thank you all for your attention. I know this was a long one. It's hard to stay focused for 2 hours, so I appreciate you staying until the very end. I want to thank again Henry Martin and the organizers of this e-learning center for this amazing opportunity to speak to all of you today. Yeah.
All right. Thank you so much for the insightful and inspiring presentation. We really appreciate the depth of knowledge and expertise you have actually brought to us. I mean, I really enjoyed the explanation of superposition, entanglements, and I mean, it's made it easier. So your guidance has actually provided us with valuable tools and perspectives that we can take forward in our quantum journey. So on behalf of the organizers, we want to express our sincere gratitude for your time and effort as well. And to our participants, we want to say thank you for your active participation in today's session as well. The recording will be made available on our YouTube channel, which we will share with all of you as well. We encourage you to keep exploring and experimenting with what you have learned today. This is not the end. This is just the beginning, please. So kindly.
Thank you, everyone. I hope you have a great evening. And I hope you continue learning a lot in this e-learning center series. Good night.